have the podium microphone on, please? Thank you. And welcome to this afternoon's panel on dark matter particles. I thought I'd start by reminding you of the talks that we heard in the earlier session, which ended several nanoseconds ago. We heard from Elena Aprile on the next step in the search for WIMPs with noble liquid targets. Tracy spoke on what indirect searches teach us about particle dark matter. Ruben Essig talked about direct detection of sub-GeV dark matter. Konstantinos Gordis talked about new gravitational degrees of freedom as a proxy for dark matter. Andrew Long talked on does dark matter interact with more than gravity. Jens Niemeyer talked granules, solitons, and mini-clusters, axion-like particles gone nonlinear. Marco Regis, particle dark matter searches via cross-correlation between gravitational lensing and gamma rays. Cora Dvorkin, novel probes of dark matter. And Juan Garcia Valido, primordial black holes and the nature of dark matter. So in the panel today, we will talk about a range of dark matter particles, but it's a finite range. The good news is it's a finite range, going over a few orders of magnitude from 10 to the minus 22 electron volts to 10 to the 19 GeV. So we believe it has to be larger than 10 to the minus 22 electron volts, so the de Broglie wavelength of the particle can be smaller than, of the dark matter can be smaller than dark matter dominated objects. It's usually stated that the dark matter has to have a mass less than the Planck mass of 10 to the 19 GeV, otherwise you would call it a black hole. If it is a fermion, then the exclusion principle will tell us that in order to have sufficient dark matter density, the mass has to be larger than a few electron volts. We will talk about thermal freeze-out and other possibilities for dark matter. The mass has to be larger than the mass of the electron if the annihilation is the standard amount of particles. And if it is a thermal freeze-out, where the present abundance is set by the annihilation cross-section, the mass has to be less than 100 TeV or so, because otherwise the annihilation cross-section would be too small. We will talk about dark matter particles, which generally restrict us to having a mass smaller than an electron volt. If the mass is smaller than an electron volt, with the dark matter density that we need, the occupation number in a de Broglie wavelength of the particle would be much, much larger than 1, and a wave description would be more appropriate than a particle description. So this rather large range of dark matter masses is populated, maybe sparsely, but it is populated all the way across. Planktons, particles with Planck masses, or the mass of a plankton, actually. That, you know, if you go in the ocean, a plankton has about that mass. WIMPzillas we heard about, 10 to the 10 to 10 to the 13 GeV. Supermassive dark matter, masses larger than 100 TeV. The WIMP range, generally taken to be between a proton mass and a TeV. Light dark matter, larger than the mass of the electron, smaller than the mass of the proton. Ultralight dark matter, and fuzzy dark matter, having a mass down to 10 to the minus 22 electron volts. If we really had a dark matter debate with all the possible candidates, we would certainly need more than 2 nights to have the candidates debate. And dark matter particles go all the way, candidates go all the way from sub-electron volt mass neutrinos. WIMPs exist. Neutrinos are weakly interacting. They have a mass. Stereoneutrinos and gravitinos are usually modeled as warm dark matter. Lightest supersymmetric particle. The lightest Kaluza-Klein particle, which is, which have proponents here on the panel, at least 2. And these are either thermal relics or decay or oscillation from thermal relics in the early universe. Then there are dark matter candidates that are produced from phase transitions, Bose-Einstein condensates, axions, axion mini-clusters, solitons, Q-balls, B-balls, oddballs, all sorts of names. These are produced in phase transitions, and supermassive WIMPzillas from inflation. These are non-thermal relics. So dedicated theorists over 3 decades have limited the mass of dark matter between 10 to the minus 22 electron volts and 10 to the minus 8 solar masses. A lot of hard work and imagination has gone into that, giving the experimentalists a lot of guidance. And the interaction strength is somewhere between only gravitational and strongly interacting. So it's been narrowed down, and I don't know why it hasn't been found yet. Perhaps the most controversial question we will address is, are WIMPs dead, sick, healthy? And the answer to this question may depend on the answer to another question, what is a WIMP? There are the strict constructionists, the purists, who say a WIMP is a cold thermal freeze-out relic with weak scale annihilation cross-section and a weak scale mass. Then there's the liberal constructionist, Graciela, who would say anything that is dark matter particle. Axions are a WIMP, solitons are a WIMP. And the individual panelists may differ, so I'd like them to describe, if they use the word WIMP, exactly what they mean by WIMP. Other questions that may or may not be addressed by the panelists. Dark matter detection, direct, indirect, accelerator, where do you put your effort? Strongly interacting dark matter that we heard about earlier in the week, with a cross-section divided by mass of about a barn, or GeV. What do you think from a particle view? Is this a reasonable thing to assume? Warm dark matter, does it need to cold? Nothing new has been seen at the LHC yet. How much does that worry you? If there is a dark sector, what are the rules for the dark sector? What are the constraints? How do we imagine a dark sector? Does anything know? How would we be sure we have seen dark matter? If we see a signal someplace, how do we know it's dark matter? Finally, the complementarity between indirect, direct, and accelerator, I hope will be addressed. So let me just close with a slide that I got from Elena Aprile's presentation this morning. Just to get you the idea of dark matter is so interesting. A large number of theoretical groups, a large army of physicists are spending their life looking for dark matter in experiments everywhere from the South Pole to just about every continent. So this is a subject that is important and interesting and crucial to the community, and we're not ending this session until we find the answer. So let me first call on Graciela Gelmini from UCLA. After 20 minutes, you'll have any sound of the 10 minutes.
Okay, so I was asked to, does this work? Does this work?
Yes.
Okay, thank you. So I was asked to talk essentially about this, dark matter particles or not, and WIMPs dead, alive, in good shape. So dark matter particles are not that interpret in 2 ways, either dark matter or not. And in this case, so far, there are no alternatives to dark matter. We'll make a comment about it. And then particles or not. Obviously, there are other non-elementary particles, potential components of the dark matter. That's clear. For example, primordial black holes. With respect to WIMPs, well, WIMPs dead alive, it depends a little bit on how restrictive your definition of WIMPs are. I don't think that the WIMP concept includes that they are just thermal relics with the usual assumption of cosmology before BBN. I don't think that that's the case. But in any case, words evolve, and that does not held up by a word. Many models are projectors, and many are not. And I think that this discussion has an implication with respect to how to continue, for example, in direct dark matter detection. And in case I don't get to this point, because I will be cut off by our severe chair, I believe that there are mature background-free, practical background-free techniques based on xenon and argon, liquid, and other gases to get to the multi-ton scale in direct detection. And we should continue with them, giving about wrap to WIMP searches, but also diversify. There are beautiful ideas already existing, some of them proposed, beautiful ideas for lighter dark matter. They were addressed actually by Ellen and Ruben before, and Juan talked about primordial black holes. So with respect to what is dark matter, I think I will go through what I think the 8 properties. When I get to point 8, I think that this is all we know about dark matter, and anything that fulfills these conditions is a good dark matter candidate. This is what we know about dark matter. First of all, well, obviously it has attractive gravitational interaction and is stable, or has a lifetime much larger than the lifetime of the universe. It's obvious it has to be around. Dark matter is clearly non-baryonic, and that means it doesn't participate in BBN, big particle synthesis, and it is not observed to interact with light. It doesn't mean necessarily that it doesn't have any interaction, any electromagnetic interaction. It could have a small enough charge, like for example a really charged dark matter, which then would be naturally a member of atomic dark matter or even mirror dark matter. Or it could have a small electric or magnetic dipole coupling or a nanopole coupling. And I will return towards the end to a dipole, possibility of a dipole coupling. So far, we have only dark matter and not modified dynamics plus only visible matter. And the issue is that after 2013, when we have precision data about CMB, angular power spectrum, and also baryon acoustic oscillations, there have been no alternatives to dark matter that can explain these observations. And I think it's clear that from any theory that claims to replace dark matter, we should ask for its predictions of the power matter spectrum and the fact that they should actually fit well this precision data from the early universe. And we should, I think, stop discussing endlessly only about galaxy rotation curves. This is not the state of the game any longer. And actually, Konstantinos Skorkis presented an idea on how to, maybe, he's trying to produce a model, which is a weird model of dark matter, to reproduce CFB and baryon acoustic oscillation, because there is nothing else that works, and then to somehow make a transition to a Tebes model. Let us see if he succeeds. But this idea was eloquently expressed actually by Dan Hooper in his talk in defense of dark matter, that actually you can view in the KITP website, and KITP Santa Barbara, in debate with Eric Verlinde. And in particular, I would like to mention that emergent gravity, that is what he's, the theory that he is proposing, has no cosmology. Therefore, there is no claim potentially in this theory, at least at this stage, to be a replacement for dark matter. The bulk of the dark matter must be nearly dissipationless, but maybe a little bit of it, maybe less than 10% will be dissipative. Dark matter has been mostly assumed to be collisionless. Actually, CDM should be called CCDM, collisionless cold dark matter. but huge self-interactions are possible, and actually the upper limit on the cross-section over mass and the mass ratio is a barn origin. You know, a barn is a big building that was supposed to be a big cross-section. This is a big cross-section. And actually, uranium-235 neutron capture, just to have an idea, is a few barns, neutron capture. So if you have a 100 GeV particle, this would be 100 times larger than the largest cross-sections that are in nuclear physics. So it's a lot. And of course, if you are much below this boundary, then self-interacting matter is completely indistinguishable from collision, let's call this matter. The mass. Well, yes, so our chair has already said, actually we have constrained the mass of the major constituent of the dark matter by 90 orders of magnitude, actually. On one extreme, you have, where is this? On one extreme, of course, so on the one side you have fuzzy dark matter, on the other you have MACHOs, massive astrophysical compact halo objects, of which actually you can only form in sufficient amounts if they are primordial black holes. Thank you. But of course, primordial black holes, I don't need to explain what primordial black holes are in this audience, I think. But there are many more limits, because these primordial black holes, of course, are black holes. So for example, they evaporate if they are under a certain limit. Many of them have been revised after there was this idea, a little bit outlandish, I would say, but maybe, that the LIGO-Virgo observed black hole mergers are actually mergers of primordial black holes instead of being stellar black holes of a stellar origin. And that has generated an enormous interest. And here you have a collection of limits on the fraction of primordial black holes in the dark matter over a large range of mass given in solar masses units. And then I put here in with dashed lines all those that have been revised, weakened. Essentially, this is one. Actually, this is a limit that I got from this Subaru hybrid subprime camera limit, recent publication, but even I took out one in Polensing. So here it is. Juan mentioned in his talk actually that there is, and this is for single mass, I should say, assuming that all black holes have a single mass. Of course, if you start, this is not a very realistic assumption actually, so if you start going out of that, then the limits change. But here you have, you can have the whole of the dark matter, even with this simple assumption of a delta function as a mass function. Of course, if you have a mass function at this extent, it will be even more possible. So, okay, thank you. So the other last two is that the bulk of the dark matter is cold. I don't know if collisionless or self-interacting or warm. And we don't have any cold or warm particle in the standard model. And therefore, we need beyond standard model physics in order to account for a particle dark matter. And this is all. I think these are properties are what we actually know. So anything that will reproduce these properties would be fantastic. So what about WIMPs? Well, there is an issue of WIMPs. So when you have an issue when you don't know something, what do? You go to Wikipedia, right? So here it is, actually, the definition of WIMPs in Wikipedia. Whoever wrote this, I at least agree with the first paragraph of this definition. I was looking for it. It's a very well written definition. I'm not sure who wrote it. In any case, WIMPs are hypothetical particles that are thought to constitute dark matter. There exists no clear definition of the WIMP, but broadly, a WIMP is a new elementary particle which interacts via gravity and any other force or forces potentially not part of the standard model itself, which is as weak as or weaker than the weak nuclear force, but also non-vanishing in its extreme. Perfect. What I don't agree is on the following. It says a WIMP must also have been produced thermally in the early universe. And I think I never understood the thermal production to be necessary for a WIMP. Yeah, Wikipedia is always right, but you know, you may disagree. In any case, actually, you would be surprised because I asked Michael Turner, who should be here someplace, I asked Mike. Mike invented the name. So you know, when you invent a name, at least initially, you know, you have some claim to what the name means, since you invented it, right? WIMP. So the name was coined in a paper, was first used by Steinman and Turner in 1985. And here you have Turner's lectures in June 1985, and here you have a list of what he considered WIMPs. WIMPs included neutrinos, and including axions, and including you know, warm dark matter, and including GV, supersymmetric particles and stuff. But immediately after that change, I think people decided, well, you know, we already have names for candidates for which we have names. We're going to use those names, and then they started to use, well, for neutrinos, we already have a perfectly good name. So neutrinos and axions and so on stopped being WIMPs, and WIMPs was for something else. But not necessarily restricted to this 1 GeV, 200 GeV in mass. That's not what they say. Now, WIMPs, at least they were occupying a lot of real estate here initially. I am not sure if fuzzy dark matter or something else was, but at least they occupy a lot. And befittingly to their name, WIMPs allow themselves to be expelled from whole regions of parameter space. And so WIMPs now occupy a little bit. The last pushover has been light dark matter. I never thought actually that WIMPs had to be heavier than 1 GeV. This was not necessarily in the definition. But now there is a distinction, right, between light dark matter that is being searched by interactions with electrons, and then WIMPs are restricted to those that can be searched with interaction with nuclei. It's a little bit artificial, but in any case, words evolve, and so, you know, language is alive, and we should adjust to that. It's perfectly fine. What I find extremely restrictive, and I don't think it's correct, is to identify WIMPs with WIMP miracles. The WIMP miracle. WIMPs have always been been able to be produced by different means. Here we have again 1988. WIMPs can be produced as thermal relics without an asymmetry or without an asymmetry, non-thermal relics, and even WIMPs could be unstable. They could be produced by others or decay to others. I think that this is. So what is a thermal WIMP? Well, this was the first thermal WIMP was a neutrino, actually a few GeV neutrino. And this is the story of thermal WIMPs, and they go very fast actually. WIMPs reach thermal equilibrium while the universe is radiation dominated. And of course, we don't know how cosmology, if this is correct, when the temperature of the universe, if the temperature of the universe has ever been larger than 5 MeV. So this is the upper limit that we get from BBM, 5 MeV. So we don't know the energy before, and of course this freeze out that happens later happens at the temperature that is mass over 20. So all WIMPs that are heavier than 100 MeV, the couple, their number is settled in a moment in which we don't know cosmology. So this is a big assumption. It enters, of course, into our decoupling condition. And then there is no particle asymmetry, and there is no entropy change. This is part of this calculation. And then we get this issue that actually the abundance is inversely proportional to the cross-section. And if you get the cross-section that is weak in order, actually you get some reasonable abundance. And this is, in fact, something like a miracle, because, of course, H depends on the universe, and sigma depends on the interactions, and they could have been many orders of magnitude away. So, you see, are WIMPs there? WIMPs are getting a bad rap, as you see. And most of them actually refer to the WIMP as identical to WIMP miracle WIMPs, right? And I believe sincerely that rumors of the WIMP miracles death has been greatly exaggerated, and in general, WIMP's death has been greatly exaggerated. So here it is. Are WIMPs coupled to the W and the Z? Even coupled to the W and the Z. Entirely rejected. Mostly, but not entirely. Are WIMP miracles WIMPs dead? No, they are constrained, but not dead. Not all of them have been eliminated. Why should we consider only WIMP miracle WIMPs? I don't see any reason. Are they associated? Because some people consider that typical WIMPs are neutralinos or something like that. No, there are many models still that could be found. So let me comment on this. The WIMP miracle is constrained by Fermi data. For example, these images, 15 stack images of dwarfs. This constrains the annihilation in the dwarf. And you see that this is sigma v, the annihilation cross-section versus mass. And everything that is below this limit is rejected. These limits depend on the mode, the annihilation mode. But, and the same thing actually can be done with positron spectrum measured by AMS. They constrain particles that the annihilation of that matter close to Earth. CMB isotopic precision, this was mentioned this morning. Constrained matter annihilation or decay center combination of after. I have one immediate comment that this happens at later times when WIMPs are much colder than they are at the moment they decouple. And so the cross-section, if the cross-section is independent of the velocity, then you have these limits apply to the annihilation cross-section that is relevant for the relic abundance. But actually, if the WIMPs annihilate in p wave, if they have an angular momentum at the moment of annihilating, that depends on the type of dark matter, then sigma v is proportional to p squared, and there are no limits then for that. But even if you consider limits, here we have actually Tracy is later, is one of the authors here. Obviously, you know, they were sort of annoyed by this issue of dead. GV scale thermal WIMPs not even slightly dead. So they don't consider actually all these limits. And here you have this unprobed window in which even thermal WIMPs, with, you know, with S wave, annihilating an S wave, they are still. There are many caveats. It could be asymmetric, non-standard. WIMPs may be unstable. WIMPs can be produced in the case of others. WIMPs could be even subdominant, and actually you can detect them in dark matter components. Which this is my 20 minutes? Okay. So I will exceed my 20 minutes, I will. So in any case, there are some neutralino models that are also below. Of course, there was a lump here that were rejected, so we have rejected many models and not others. I would like to say that we need to consider all types of interactions. And this is because the scope of dark matter particles has changed, and once you get the genie out of the bottle, you cannot put it back. Essentially, dark matter candidates were an afterthought in the models in the 1980s. They were all models that tended to solve dark matter problems. In the 1990s, having dark matter candidates for any model beyond the standard model was mandatory. And then in the 2000s, the dark matter models attempted to explain hints, and therefore they were completely divorced of any attempt to solve any of the remaining problems in the standard model. And that's led to all types of interaction with dark sectors, etc. And this has relevance even in dark matter searches for WIMPs in future direct detections. For example, the neutrino floor, which is where, here it is, the neutrino floor, where one of the major limits will come. Differential rates can be very different if you start assuming all types of interactions. Here you see one, for example, this one in particular is the one I will talk about in a second. I have a few transparency please. So this is a very different type of differential rate expected than if you have one of these is a spin independent interaction. So this is for a magnetic dipole moment coupling. And here you have what will happen. This is the discovery limit in terms of cross-section with respect to mass. In red, you have what happens with different, as you increase by factors of 10 the exposure. In red is what you get in terms of discovery reach, considering the neutrino background, and in black what you will have without neutrino background. This is for spin independent, and you see that it is severely undermined, mostly if you are here in which there is a degeneracy, less in other ranges. But what happens if you have this magnetic dipole? Well, if you are here in the, in the heavy side, you see that actually the black and red lines are the same. So essentially there, most of the events that you expect are above where you have events coming from neutrinos, and therefore neutrino background have no effect. So we should diversify. We have much better than what I can do. And I said did a very, very nice job in explaining new ideas. They are extremely creative, beautiful ideas that should be explored too. And this is my last. So I think we should continue a strong diversified program because we have no idea where the dark matter is. Direct detection with several targets and materials strategy is essential. In particular, as I said, continue with mature techniques that took so many years to develop, and they are about to reach the moment in which you get to the neutrino floor, and then your discovery reach doesn't increase as your exposure, it goes as less as your exposure, but there are many other ideas. Now, in direct detection, of course, with multi-messenger approach, although I think that there are some exceptions to this, but I believe that due to the astrophysical uncertainties, a discovery in indirect detection may constitute a confirmation, but not really a discovery of dark matter. This is my, and in collider searches, of course, we are going to be extremely happy if we get any signal from beyond the star. In any event, but if a dark matter candidate is discovered, we will need to confirm that this is dark matter by finding it where the dark matter is, in the halo of Raoult and others. So I think that's the point. We have an extremely vibrant field, and we will continue to do so for many years.
Thank you. So next we'll turn to Tim. Well, just a minute. Yeah? Okay, I'll tell you. Turner said they have to be thermal. She's not happy. While Tim's setting up, I'll also note that in Wikipedia, they have a definition of miracle as a word often used to give an impression of great and unusual value in a trivial context. According to Merriam-Webster, a miracle is an extraordinary event manifesting divine intervention in human affairs. I don't think scientists should use the word miracle, but okay, Jim, thank you.
All right, thank you very much. I have to say that when I hear Wikipedia, I think of an episode of one of my favorite TV shows where the character says, Wikipedia can be edited by absolutely anybody, and that means it always has the absolutely best information in it. You know the show I'm talking about, you know that this is not going well for that character. All right, I'm very pleased to be here. It's very nice to be at this wonderful meeting. Also very nice for the organizers to have arranged for beautiful October weather for us in Chicago. I actually know how this works because I used to live literally 2 blocks away from here. It's the ugliest building, so if you see an ugly building, that was that one. It's good to live in the ugly building so you can look at all the pretty buildings when you're in your living room. And I'll tell you that October is a month when you get weather like this in Chicago. Here's another example. It's also a month where you get weather like this in Chicago, so again, thank you for choosing it well. I have a new controversy, I realize. Something has changed since the last time I was in Chicago. I have a theory that might explain this, but I suspect it may be controversial. All right, so WIMPs. it was decided that I would talk a little bit about whether or not WIMPs are ruled out and what that means. I think there's a lot of interesting things we can learn from the nuance that comes with answering this question. This is my version of Graciella's slide. It has some of the same articles, but not all of them. Maybe this is fake news. Maybe you can take an example from the original WIMP that I remember growing up. I have to say, he persevered. I think the real question, though, is when you ask yourself, are WIMPs ruled out, what is really behind this question? And there's a few different components to it. The first one, as Graciela and Rocky both identified, is the relic density. Most of the WIMPs are correlating null results for searches with the relic density. The relic density, based on a standard cosmology, is clearly a very attractive target. It is worth remembering, as both of them also pointed out, that typically freeze-out occurs at energy scales that we haven't really probed directly with cosmology. So there may be room for surprises there. And my attitude for a long time has always been that this kind of standard cosmology is something that we want to establish, maybe actually by understanding the density of dark matter rather than assuming from the initial conditions. So this is contrasted with WIMP searches. Actually, I should have said dark matter searches because I did include the self-interactions, which are a very important part of the searches. But indirect detection, collider searches, and direct detection, we've already heard something about all of them and quite a bit of detail this morning. I'm going to go through those really quickly and just give some perspective. So this is a plot that Elena showed us this morning. It shows the limits on the dark matter nucleon spin-independent cross-section as a function of the dark matter mass. The famous neutrino floor is down here. You can see limits from different experiments as well. They're taking a very relevant fight out of parameter space for masses, especially above around 10 GeV or so, but extending really down to 1 GeV. We also heard in a few talks this morning that there's a ceiling. These limits become ineffective if the cross-section is too large, and that's because basically the dark matter loses too much energy on its way down to get to a detector that's underground, or maybe even on the surface of the Earth. And then the neutrino floor, it will eventually change the nature of looking for dark matter in this way when these detectors become sensitive to neutrinos. Good. So if I think about an electroweak cross-section, electroweak cross-sections live somewhere up around here in this parameter space for a typical particle that's literally charged under the weak nuclear force. This is a parameter space that was ruled out a long time ago for a wide variety of masses. CDMS, I think, touched it. I have to confess, I wasn't really in this business back then, so I might have this wrong. But I think around the year 2000 was when we sort of first knew. Graciella's nodding, so that's a good sign. If we ask what's happening now, we can actually extrapolate these curves rather easily because the scaling behavior here is just really controlled by the density of the dark matter around us, which we know reasonably well. And you conclude that actually we now exclude from about 1 GeV to about 10 to the 7 GeV. So if it's literally electroweakly interacting and is exchanging Z bosons with the nucleus, it's actually pretty ruled out. We also have searches through an indirect detection, so this is looking at the dark matter annihilating and then looking for the visible products that occur there. Again, if I assume the dark matter is interacting electroweakly, this kind of has two different behaviors. For low masses, where we're trying to annihilate through an off-shell Z boson, the cross-section is growing, and that's because the Z is getting closer and closer to on-shell as the dark matter gets closer to half of its mass. Sorry, equals mass. And then once we get to that threshold, where the dark matter is equal to the Z mass, things kind of turn over, it scales like 1 over the mass squared, and you also open up a new channel where you can actually just produce the electric bosons directly. And this has been put on top of the limits from the Fermi lab, looking at dwarf satellites that have been stacked. With 6 years, there are pretty impressive limits here. They start sort of around 10 GeV or so, where you have sensitivity, and they cross the naive thermal relic somewhere around 100 GeV. There are two places where actually you would explain all the dark matter very naturally, and again, this is a very sort of hand-wavy thing. I have to tell you more about the actual details of the dark matter model to make this really precise. But down on the lower end, we have what is the modern view of what we would call the Lee-Weinberg bound, and up at the upper end, we have something that looks like the targets we get for Higgs-Zenos or WINOs. And so this is clearly saying something very interesting about dark matter that interacts electroweakly. We also have important limits from the CMB. They were also alluded to this morning. And again, I've just put the same electroweak in quotation marks cross-section here. And we see that for a wide variety of channels that things can annihilate into, we are actually sensitively probing dark matter. And then finally, accelerators can also produce electroweakly interacting particles. Here's a search by the ATLAS collaboration, but you can find very similar ones from their sister experiment, CMS, where what's happening is the Large Hadron Collider is colliding protons. It's producing some particles with electroweak charge, which are then decaying into stuff that includes perhaps an electroweakly interacting dark matter, and also some visible decay products from W bosons that happen in the decays. And this takes a bite out of the parameter space that lives in the mass of this parent particle, the charged one, and the mass of the neutral particle that looks something like this. It's largely constrained by just where they have energy to produce these things efficiently. And with some backgrounds that matter too. So what does this mean by WIMPs? Well, of course, it depends what you mean by WIMP. Up until now in this discussion, what I've done is I've tried to use the definition of WIMP that no one could ever possibly disagree with, right? It's a particle that interacts electroweakly. And it looks like actually those WIMPs are not in good shape. Of course, that's not the only definition, and it's not even really the one that I operate with on a day-to-day basis. So let's say a little bit more about how that works, because I think it's interesting if you push into it, you realize that maybe things are not as bad as they seem. And it also is instructive in terms of telling us what these experiments are really teaching us. So all the assumptions that underlined the previous discussion were that the dark matter was interacting through a Z-boson exchange. We learned in particle physics kindergarten the Z-boson exchange can be written, the Z-boson interactions for an electroweakly charged particle can be written in terms of its weak isospin and its electric charge, but luckily we know the electric charge of dark matter, so we don't have to worry about that. This is exactly, for example, what you derive if you assume the dark matter was a neutrino. So it also suggests, though, that if I don't want to have this happening, and really the direct searches are telling me that I can't afford to have it happening, one thing I could do is just make sure that T3 is equal to 0. In other words, make sure this particle has third component of weak isospin equal to 0. And then I don't have Z couplings at all. This actually happens for the odd dimensional representations like the triplet. That's like the we know of supersymmetry. The quintuplet. It doesn't work, though, for things like doublets, so it doesn't work for neutrinos, quadruplets, etc. Another way to say this is that dark matter should not be carrying hypercharge, and that's just because charge is related to T3 and hypercharge. What this tells us is that if I'm going to have some particle that is electroweakly interacting and yet does not couple to the Z boson, it has to be part of a non-trivial representation of the SU2 interaction of the standard model, which implies that there are charged particles that come along with it. In the triplet, that's the smallest representation that I said works, I have the T3 equals 0 particle that could be the dark matter, but I also have the T3 equals -1 and 1, which together form electrically charged particles, whose masses can only differ by about 100 GeV or so, and that's because the electroweak symmetry would dictate that they have equal masses, but of course the fact that that symmetry is broken by the Higgs tells us by how much that expectation can be violated. We can also think about this fruitfully in the language of effective field theories. Just for illustration, this is just quarks and gluons. You can write them down relativistically or non-relativistically. If you want, these are more realistic in the sense that they know that relativity is a thing. These are more useful because actually that's the natural language for the scattering problem. And in the non-relativistic way, one of them turns into the others. The problematic interaction is the spin-independent interaction. That's the one for which there are the best bounds from direct searches. They correspond to a handful of the relativistic side, and then there's another couple that correspond to spin-dependent. So that already suggests something about a more generic WIMP. If we have particles that like to interact with just these non-circled interactions over on the relativistic side, we're going to have a signal for direct searches which are velocity suppressed and therefore weaker, which does not at all mean not important. And one very simple thing you could do would just be to argue that the dark matter is a Majorana particle. So the vector interaction vanishes, the vector interaction, which was this one up here, which mapped onto this independent cross-section, vanishes identically for a Majorana particle. And what that leaves behind is only things that are spin-dependent or velocity suppressed. So another strategy for electroweak charged WIMPs would be make it Majorana, don't make it Dirac. That means that you're going to have spin-dependent scattering with nuclei, and you'll have weaker constraints. Now, of course, if we look at constraints on the spin-dependent cross-section, in this example from Lux, what you see is that actually, even for an electroweak sized cross-section, that still rules out a huge amount of parameter space. Right? It no longer goes to 10 to the 7, it only goes to 10 to the 4 or 5 or so. But still, actually, just making your particle Majorana is not actually sufficient to save it. And another thing I should mention is that even if you do manage to switch off the spin-independent cross-section, it's very often the case that when one looks at loop-level scatterings, one actually generates a spin-independent cross-section again. Even if the tree-level interaction, so let's say I've got a Majorana particle, its tree-level interactions are only spin-dependent. The quantum field theory tells me that at higher orders in perturbation theory, there's an interaction like this. It's suppressed because it's a weakly coupled loop process, so it's like 1,000 times smaller than the spin-dependent interaction was at tree level. But actually, if you look at the maximum sensitivity, the Zeeman limits on spin-independent scattering are something like 10 to the 5 times better than spin-dependent. So also, this is something that has to be taken into account, and typically, just turning off the spin-independent cross-section is not actually going to make you make the direct searches insensitive. And then a final strategy I wanted to discuss, purely in the electroweak sector, is you could actually construct a dark matter particle which is a mixed state of more than one kind of electroweakly charged object. In that case, you could arrange for cancellations between the different contributions to the coupling, though that's not generic. I don't know of any theory where this is actually the dominant scheme that people use to avoid constraints. I guess maybe the blind spots have some character of this. So the MSSM, the minimal supersymmetric standard model, does benefit to some degree. But mostly the supersymmetric model survives by just having a large component that has no electroweak charge. So the dark matter in the minimal supersymmetric standard model is a linear combination of a bunch of gauge eigenstates. And what they really just are largely arranging is to have a component that's very large that doesn't actually interact electroweakly at all. And then final thing I wanted to say about heavy electroweak WIMPs is that indirect detection also has some very interesting features. As I go to very large masses, there are Sommerfeld-like enhancements and resonant enhancements. This was actually done very nicely in this paper by Tracy. And you can see that actually because of the interesting structure in the cross-section, whether you're ruled out by searches for gamma rays produced, gamma rays observed, say, by the Hess telescope, really kind of depends on where the mass is, and it's not totally linear. You are ruled out all up to here. Then you get to a little region that's maybe not ruled out by the current data, though it should be soon. And then as you get into the places where the cross-section has fallen more, naively you're ruled out over here to the left, the larger masses, but there are still actually magic points where the cross-section is very enhanced, and there is still something you can say. So if I were to put this together into a scorecard, the electroweak charged WIMP is ruled out by a variety of different things, including searches involving gamma rays. So that is very effective around 100 GeV. It peters out sort of around a few TeV, but there are still some points where it's effective. The CME covers the low mass region pretty nicely, and nuclear recoils are really doing wonderfully. But even just something like a Majorana electroweak charged WIMP, I actually changed the picture quite a bit. Now the nuclear recoils are really just telling me about spin-dependent interactions, so it's a much smaller range of mass. And the gamma rays similarly actually have a suppression because the annihilation cross-section is usually P-wave, or goes like the mass of the particle is annihilated. So I wanted to use the last couple of minutes to say something about less obvious definition of WIMP. So this is a kind of weakly interacting massive particle. It's not literally charged under the electroweak force, but it has, well, what can I say? It agrees with the definition in Wikipedia, maybe. There's a big playground. This is a plot that I made in SNOMAS to try to show the relational relationships between different theories of dark matter. Somebody promised to make it into a stained glass window, but he never did. It was interesting, and I think it taught me something. What I would realize now, though, is if I were to try to make this plot again, because we have sort of moved into a phase where a lot of our theories of dark matter are more designed either to explain phenomena or to test ideas, I would probably have to make this Venn diagram three-dimensional. So somebody in Snowmass 2021 can have good luck doing that. So of course, once I go beyond the electroweak bosons as being the mediators that can allow dark matter to communicate with the standard model, the focus shifts naturally to the relic density through freeze-out, and I think that's why the Wikipedia article actually mentioned it. And the reason is just that you lose a lot of guidance. The electroweak bosons have interactions that are determined by the gauge structure of the standard model, and so there's very little you can really argue with about them. Once you have new particles, there's actually quite a bit more. So couplings are typically now free parameters. The constraints from direct detection are still very strong in general, and unless something mitigates them, they often rule out cross-sections that are necessary. They should have been for freeze-out, actually. And things become much more model-dependent. So let's just talk about a few strategies that I see in the literature. So one thing is, we could, instead of invoking the W or the Z bosons as the mediators, we could use the Higgs boson. Unlike the weak bosons, the Higgs coupling is not specified in terms of the parameters we've already measured, so it's a lot more free. It's very unlikely that the Higgs is the source of mass for dark matter in the same way that it is for the standard model particles. If that were the case, the direct searches would have probably discovered it. There are lots of variations to how to make this work, so you can have just the dark matter interacting through the Higgs, with the Higgs, with basically H dagger H, and then I replace one with a vacuum expectation value, giving me dark matter interacting with Higgs. You can do the same kind of thing with fermions. Maybe there's some particle that was integrated out along the way there. You can have mixing between the Higgs and some other mediator, or you can even have radiative processes where the dark matter interacts with the Higgs. And all of these things are represented if you look on the archive. Higgs exchange is still something that leads to direct a signal of the direct searches. This is a plot that was done by Richard Hill and Mikhail Solon. What it shows is that at loop level, a dark matter particle is electroweakly charged. Even if it has no interaction with the Higgs at tree level, we'll still pick one up at loop level. It'll give you, though, a very suppressed cross-section. Typically one that's actually, this is as a function of the Higgs mass, and so I should have mentioned that the actual Higgs mass is somewhere around here. This will typically give you a cross-section that's rather suppressed. It may be hard to find it. You also see strategies used in the searches themselves. This is a search that was done by the CMS collaboration at the Large Hadron Collider. What they're doing is they're trying to produce the dark matter's mediator, which they assume is some kind of Z prime, some kind of new gauge force that's very massive. It decays into the dark matter. There's also a jet of hadrons produced. So that gives you something you can see. And they rule out a parameter space in the plane of the mediator mass and the dark matter mass. But they made some very key assumptions here. They decided that this particle has axial vector interactions. This gives you a spin-dependent cross-section at tree level. Right? And they did that precisely because they knew it was ruled out otherwise. Also notice that these plots tell you what the couplings that they chose for the mediator with quarks and dark matter is. And this plot is totally dependent on those choices. So you should always keep that in mind when you try to draw conclusions from it. You could look at something like a pseudoscalar, something like the axion, or a cousin of the axion is the mediator. It leads to interactions which are both spin dependent and also velocity suppressed. Therefore, the direct searches have a great deal of difficulty probing theories like this. This is just as an example. These are two plots of the spin-independent cross-section as a function of the mass of the dark matter. There's some points here that would explain the galactic center excess that Tracy talked about this morning. They're all very handily ruled out by both Lux and Xenon. If I move to pseudoscalar interactions, I can still describe the galactic center excess, and Darwin would even have trouble finding some of these points. And finally, I can imagine that the dark matter, rather than talking directly to the standard model, goes through some particle which couples relatively strongly to the dark matter, but couples very weakly to the standard model. So maybe the dark matter annihilates by producing these on-shell mediator particles. Maybe these last for a kiloparsec or something before they decay. That's plenty of time for us to be able to see what they're producing. But on the other hand, it would lead to a very, very suppressed rate of direct scattering. This is just a plot that shows you sort of how the mass, how the energy of the final state standard model particles correlates with the mass I choose for the mediator So the outlook, are WIMPs dead? I think the answer really depends on how you frame the question, so it always comes back to what is a WIMP. But some of them are. Electroweakly charged particles are rather constrained. Some options survive by making choice of electric representation or spin. Others are not really ruled out. Freeze-out relics can exist for a wide variety of masses. Engineering may be required on the theory side, but that just could be how nature works, and it could be that that's what we're actually learning from this program. Or put another way, we've learned a lot about what WIMPs are not. Rocky actually challenged us to answer the question, where do you put your effort? And it's very clear to me that the answer to this question is yes. Thank you.
Okay, let's hear from, oh, they want to take your, hear from Catherine Turin, please.
It's not connected, I swear. It's a miracle.
So we've been talking about a lot, the WIMP, what is it? Is it dead? And whether that's a meaningful question to ask because language shifts over time. From my perspective, the meaningful thing in that discussion about language is what is it that you decide to build? Okay, you have an experimental community, they're looking for things, and in my mind, the reason why the language WIMP is useful is because it defines something that gives us a target. Okay, and so I want to kind of focus on it from that point of view, from that observational point of view. How do we probe these candidates? And then ask the question about, where are we going to put our efforts going forward as a community, given the fact that we have this big open question. So I'm going to devote exactly one slide to the question of why are we talking about dark matter as opposed to modifying gravity. And the fact of the matter is that it is the only paradigm for understanding all the observations that we have of the universe from the time that it's a second old. So, from the time of Big Bang nucleosynthesis through CMB, large-scale structure formation, acceleration of the universe, and galactic rotation curves, all these things are only understood within the context of the dark matter paradigm. And of course, that's the reason why we're devoting all this effort. So, we've seen this big arrow. I'm going to have a little bit different take on it because I want to focus on it from an observational point of view. So the WIMP, in my mind, and I'm going to tell you why I think about it this way, is defined in terms of specific targets that experiments have been going after single-mindedly for decades now. And I think it's been really important to go after those. But it's time to broaden, I think. But as we know, the panorama, what's consistent with observations, is from all the way down to 10 to the minus 22, 10 to the minus 23. What's an order of magnitude change when you're talking about something that's spanning 90 orders of magnitude up to 1,000 solar mass, which is about where the limit is from the Lyman alpha force, just from how clumpy that we know the dark matter cannot be. Okay. So the WIMP paradigm, specifically, that's a weakly interacting massive particle, so I really mean interacts with the standard model via the weak force, has good things going for it. They give the right scale for the abundance, for cosmology and detection. It's that trifecta. It's the abundance, cosmology, and detection. So if you just do some back of the envelope estimates, and you compute the interaction cross-section by the Z boson, it's really big. It's way above what's currently constrained in direct detection experiments by many orders of magnitude. Okay, so that's the detection side of this. Then there's the abundance side of it, that if you look at the annihilation cross-section of this particle, and you again do another order of magnitude back in the envelope estimate, you come up with this 10 to the minus 24 centimeter cubed per second, again, right in the right range for the abundance, and also something that can be detected and constrained. Now, the other important aspect of this that's formed the cosmology is that these cross-sections are too small to have any relevant impacts on structure formation. So I think this is something that people kind of neglect or goes unsaid, is the fact that these typical interaction cross-sections are many, many orders of magnitude below what would leave imprints on cosmological scales, is the reason that I think over the decades we've kind of let the cosmological observables kind of go by the wayside, and have really focused on indirect detection, direct detection, and production at the LHC. Now, as soon as you start to relax a little bit, the weakly interacting, the fact that you're going to put this mass scale near the weak scale, then all of a sudden those assumptions go away. Okay? And now cosmology just very generically becomes much more interesting for signatures of dark matter. Okay, so the WIMP, as we've heard, is not dead if we define it in the strict sense of the weakly interacting particle. It's not dead. We've seen this plot now. If it interacts with the Standard Model via the Z boson, that's pretty well ruled out. We're still probing the Higgs interacting dark matter. That's what this blob is. But the reason why I think the WIMP as a language being well defined is because of these targets. All these experiments have been focusing on this window where dark matter interacts with the Standard Model, typically with the Higgs boson. And there are still important targets to go after. So I want to just emphasize one. Tim touched on this a bit, but I think it's worth emphasizing a little bit more, that the pure neutralino doesn't couple, will not produce a candidate at tree level in this blob of Higgs interacting dark matter. And if you look in the context of supersymmetry, it's easy to understand why that is. The rules of the theory don't allow you to write that down, but you do get a one-loop process. So the classic example of this is the WINO. However, I don't mean to be a downer here. The WINO is close but no cigar. So if you look at, Tim also showed a cousin of this plot. The interaction cross-section of an electroweak triplet, that's the WINO, is a function of the mass. So a thermal WINO has a mass of about 2.9 plus or minus 0.1 TeV. So you can pick that up on this plot. It's right here. This is the interaction cross-section, and here's a bunch of projections. Okay, so xenon n ton. I don't know if LZ is on here, but Darwin is all the way down here. So if you try to take 2.9 TeV and look at what even Darwin is going to be able to do, it's not going to be able to rule out an electroweak triple, the WINO. Okay. On the other hand, we also have indirect detection signals. So this dark matter can annihilate to Zs and photons, and that can produce a signal. So here already, this is the annihilation cross-section of an electroweak triplet. As again, is a function of the mass. So thermal guy is going to be sitting here right close to 3 TeV. And these are the current constraints from Hess. It's an Arrow-Cherenkov telescope for different profiles. And you can see that an INASTO profile is very handily ruled out for a 3 TeV WINO. You actually have to core the profile quite a bit before you can start to make things consistent with the current Arrow-Cherenkov constraints. Remarkably, even the Higgsino, okay, these are dark matter candidates that you don't have any hope of seeing at the LHC. They're just too heavy. They're only electroweakly interacting. Even the Higgsino, which has a smaller annihilation cross-section, you can get some reach with CTA in the future. So this is an NFW profile. So here again, Higgsino dark matter, thermal dark matter has a mass around a couple of TeV. And you can see that CTA here for an NFW profile is going to have reach to this dark matter candidate. However, these candidates that interact through a one-loop process, I do not think are the case for going to even larger detectors than n-ton. Okay? So that's just that reach going forward. Okay. So there are still interesting things to look for in the area of WIMP detection. I think just broadening the WIMP definition endlessly is not helpful from the point of view of detection, the fact that we're going after particular benchmarks. But I do think that as we broaden this out and think about other dark matter candidates, that there's a lot of complementarity between these different detection methods. So in the case of heavier dark matter, you can set the relic abundance through interactions with the standard model, but it's challenging. So we heard a talk this morning about how you can set it gravitationally. At these heavier masses, detections through the standard model interactions is generally not motivated by abundance. On the other hand, you can imagine trying to look for them through purely gravitational interactions. Okay, that's going to be hard. There are some people, some brave souls who are thinking about it. I think there have been some talks here about that. I think that's a thing into the future that we should be thinking about more. Dark matter substructure, we heard a nice talk this morning from Cora talking about how we can use various types of substructure, measuring dark matter substructure to try to get a handle on dark matter. That's really relevant at these higher mass scales. And then, on the other hand, you can look at the very low mass end. So below an electron volt, as Rocky alluded to in his opening talk, the dark matter behaves more like a wave than like an individual particle. There's a lot of very interesting techniques to search for dark matter using the coherence that's inherent in the fact that the dark matter is a wave. And then you have this intermediate regime, where the observation is via particle interactions. So you don't get this coherence of it being a wave. The dark sector here, okay, I'm already broadening the language, is still highly motivated. It's not detectable with the traditional WIMP experiments. And this is the reason why I think the language is important. Is because we have built experiments and we've devoted a lot of experimental effort into detecting dark matter in a particular mass range with a particular interaction cross-section with a particular annihilation rate to standard model particles. However, if you just broaden this out, okay, and consider now dark matter particles that are not motivated by solutions to any of the problems of the standard model, still, in many cases, their abundance can be set by interactions with the standard model. And so you can still have very well-motivated particles that give definite benchmarks. And I do think that for building experiments, benchmarks are important. You have to know that there are theories that make sense and that you're probing in a meaningful way. So as a general rule, now, unlike for the case of the WIMP, dark sector dynamics are complex, and they are astrophysically relevant. And the simple reason is just that if I take this mass scale and I lower it, this cross-section goes up. So now if what I can probe astrophysically is something that's more like a strong interaction cross-section, that's not hard to do if instead of the dynamics being at the weak scale, it's brought down a couple orders of magnitude. The abundance can still be set by a thermal process, if that's what you want. It doesn't have to be. Typically by just lowering this coupling constant at the same time you lower the mass scale. So you can still get this typical annihilation cross-section out. You just lower these two things together in tandem. Still perfectly natural dark matter models. And so I think what's happened, I've been showing this slide for much longer than I care to think about. But I do think from a conceptual point of view, what's happened is that now as soon as we stop making the dark matter sector parasitic, it takes on its whole own life. And now you're just free to think about a lot other kinds of mechanisms for setting the dark matter density. And that was really the essence of Tim's Venn diagram, was to show that as soon as we start to think of beyond the WIMP paradigm, theories of dark matter broaden out a lot. So I think what in the last 5 years, the 5 to 10 years, the thing that's really been an important development is what are you going to go and look for, and where are people going to put their time resources going forward. And it's this fact that the sensitivity of these experiments has taken a nosedive, up until the last several years around this 10 GeV mass scale. And there are a lot of neat ideas for how you can search for dark matter at this low mass range. Ruben talked this morning about a number of them. Some of them are being funded now. Sensei and DAMIC are two examples that are moving forward. Super CDMS has a lot of effort on looking for light dark matter. Xenon has done some analyses with electron ionization. I want to talk about one in a little bit more detail. So just to give you kind of the picture, the traditional WIMP, the effort in the direct detection experiments has been to search for dark matter with mass above about 10 GeV. Then as you lower this down to a little bit, down to the MeV scale, semiconductor probes, so we heard about DAMIC and Sensei this morning, are sensitive to dark matter down to the MeV scale. But then of course you can continue down by many orders of magnitude. So dark matter, which is consistent with the with structure formation, should typically be heavier than about a keV if it has a thermal abundance, or thermal here is defined broadly. And then you need different kinds of ideas. And then below the keV scale, dark matter can be bosonic, and in principle you can detect it through absorption processes. So taken together, you can actually have a suite of experiments. And how much time do I have? I have 5 minutes. I have an infinite amount of time. So I want to talk about one of these ideas, polar materials, which is complementary to the ones that Ruben talked about this morning, which are semiconductor targets where you excite electrons. So why is it that you have to, as the dark matter gets lighter and lives in a hidden sector, why is it that you have to look for qualitatively different kinds of ideas? And the basic reason is just that the WIMP is kinematically well matched to nucleus. So, you know, the fact that weak scale is around 100 GeV, which is around the same mass as typical nuclei. That was a coincidence that happened to work out nicely for direct detection. But as the dark matter gets lighter, what you end up happening is you look at the energy deposition as a function of the momentum transfer, and nuclear recoils just do very poorly because of the kinematic mismatch between light dark matter and a target nucleus. And so they're only good targets for the WIMP. If you look at lighter dark matters, MeV masses, as we heard from Ruben, electrons are good targets. Now the new conceptual thing is that once dark matter drops below an MeV, you actually need collective excitations in these materials. So that's what's happening. What do I mean by collective excitation? Well, collective excitation, broadly speaking, is a phonon. Phonon or spin excitation. And the physical thing that's happening is once the dark matter gets lighter than about an MeV in mass, its de Broglie wavelength is longer than the typical interparticle spacing in some materials. That's the basic physical fact, and therefore the relevant degrees of freedom, if you think about it from an effective field theory point of view, are collective excitations. Collective excitations are phonon modes, and I'm not going to go through any of the details of these calculations, but they depend on what kind of material that you're looking at. And so one of the things that I find really nice about this is that you get a complementarity. And the plots that we've all seen for WIMPs start at 1 GeV and go on up. And now there have been a suite of experiments that have been built out or proposed. Some of them are being built out. So Sensei and DAMIC are both moving forward, Super CDMS as well, to search for dark matter that's as light as an MeV mass scale, and then going all the way down now to a keV scale using phonons and electron excitations in small gap materials. The other thing that I want to point out this was also shown a couple times in the morning session, that there are these well-defined targets. Now they're not thermal, but the abundance is set by coupling to standard model particles. And they give well-defined benchmarks. I would not call this a WIMP benchmark. There's no weak interactions. There's a massless particle that's kinetically mixed with the standard model, theoretically very simple. I think the important point is that there are things that you're aiming for. And that's theoretically, conceptually distinct from the push of the field for WIMP particles. Okay. And now this is part of an entire ecosystem new ideas. So people, I guess, vote with their feet. I would say that this is a very healthy field. As we think about what do we do, I think after the N-ton experiments, after LZ or Z-non N-ton, I guess one of the things that we can talk about is, do we as a community want to build Darwin? How much further do we want to keep going with the WIMP? Okay? And how much do we want to try to think about building more experiments that are probing at qualitatively lower mass scales? There has now been a community movement on this that have crystallized in some additional R&D funds available for experiments that are looking to create dark matter accelerators detected underground through individual particle interactions. So this is direct detection and then detected if it's a wave in perhaps some type of a cavity experiment. But I do think that there is an important paradigm shift that has happened. Just if I think about this in terms of what kinds of experiments we're building, and hence what kinds of dark matter candidates we're going after. So, the first thing we realize is that, the universe, there's a lot of matter out there that we don't have a theory to describe. Then we went after particles with mass near the weak scale that interact through weak scale kinds of forces. And there was a lesser focus on axions. And I think what's really shifted in the last decade is this idea that we should go for, we should be ready for anything else. The dark matter problem is not going away. We should be thinking about a broad class of models, but at the same time, we should be motivating them theoretically from all of the information that we have cosmologically. So I'll stop there.
So we do have some controversy, some disagreement in the panel about the meaning of a WIMP. And there's no controversy? Okay. So we have a proposed particle called a WINO, which is a supersymmetric W. Maybe we need a WINO, which is a WIMP in name only. Okay. Let me ask, so nothing new has been seen at the LHC yet. How nervous does that make you, or disappointed or surprised? Graciela?
Pretty nervous. I'm not sure if surprised, because after the Higgs, there's no clear, there was a no-loss theorem for the LHC before the Higgs, because we knew that actually, if you have the scattering cross-section of WW1 to WW, unless you have something else that contributes at the electroweak scale, at some point below TV, you break unitarity, so you have to have something. And so there was this guaranteed discovery at the LHC, and the LHC has made it. Now, there's no guaranteed discovery. But of course, we still think that the standard model cannot be the last word. And if you look for things, you will find it. So the LHC can still find models, not the easiest models. They would be models that tend to be a little hidden with respect to the LHC, but who knows what nature chooses. So, for example, constrained spectra, compacted spectra in which the masses are very close, and so on and so forth. So still, but there is no guarantee discovery. So yes, it is even more worrisome how we are going to move forward. If,
the connection with dark matter.
The connection with dark matter is, of course, that the LHC can do some things. It would be fantastic to have anything. But if there is, at any rate, any hint ever of something that could be a dark matter particle, the LHC, we will love to have this problem. But in any case, we will have to prove that it is a dark matter, right?
Yeah. And Tim, you're either a collider physicist or a recovering collider physicist. I'm not sure which. What's your take on nothing new seen at the LHC?
I think maybe recovered. It is worrisome in the sense that I think many of us were hoping that the LHC was going to see something beyond the Higgs boson. And going forward, right, the LHC is far from over. It's going to run for at least another decade. We're past the point where we're going to see big increases in sensitivity just based on the fact that we're turning it on and exploring a new energy for the first time. So if nothing changes, that means we're going to look at more sort of square root of n type advances. That said, though, increases in understanding of the backgrounds, increases of experimental technique, they can actually be transformational. So I'm still avidly watching what the LHC is doing. I'm not sure I ever thought that the LHC was guaranteed to find anything out about dark matter, and so I guess I'm just, I'm going to wait and see.
Well, not necessarily find anything about dark matter, but find something that's related to the physics at the dark matter scale.
Right, sure. Whatever scale that is. Right.
And Catherine, you mentioned at least accelerators, fixed target experiments and things like that. Do you want to expand on that? Do you think that's the promising way to go?
I think it's one promising way to go. So it's on the accelerator side, it's the analog of searching for MEV scale dark matter indirect detection experiments. So seeing something in these experiments relies on them having a certain size coupling to the electron, typically to the electron, with the density, and the size of that coupling being set by, say, hypothesis of a thermal WIMP, with the freeze-out cross-section, which would imply a certain production rate at these accelerators. These are relatively low-cost experiments, and so I think from that point of view, broadening out the range of collider experiments, I think, is a well-motivated thing to do, and something that should definitely be pushed forward. I should say, just to come back to being concerned about the LHC. The LHC saw kind of exactly what we expected it to see. I mean, in some sense. Yeah. So if you and I can remember having this conversation with fellow students in the early 2000s about, what do you think the LHC is going to see? And my answer at that time is, well, LEP didn't see anything. And LEP has made all these beautiful precision measurements of loop-level processes, amazing flavor precisions. We already have to work really hard to evade all those constraints. So what do you expect the LHC to see? I would have said, expected to see standard model Higgs.
Well, to be fair, confirming the standard model of particle physics is an incredible accomplishment.
It is. It's an incredible accomplishment, and we probably should not have backed ourselves into the corner of this idea that it wasn't an amazing accomplishment. But the LHC, was amazingly successful, including at seeing what we expected it to see.
So if next year Elena sees something, some candidate events, how do we know she's seen dark matter?
We won't right away.
Oh no, you need at least 2 targets in direct detection. This is the first thing. That's why if you go to the multi-ton, you should go to multi-ton, as we were commenting, at least with 2 targets, argon and xenon, at least. You need 2 independent discoveries, either in or it could be indirect or 2. It's not entirely given, as we heard. There hasn't been sort of a signal of dark matter from the galactic center, but of course you can say that there is dark matter there. But it could be confirmation.
I do think one of the interesting things about kind of switching from weak scale dark matter to lighter dark matter is that that these experiments are actually very naturally directional. And so it's possible with a single experiment to orient your target, your crystal, with respect to the wind, and you'll get order 1 daily modulations. So we happen to have gotten sort of unlucky with nuclear recoils because the target itself doesn't, by its essence...
Well, there are seasonal variations at some level you might expect.
There are seasonal variations, but they're much smaller. And it's going to take a lot longer to.
We're going to turn to the audience in a minute. I see Elena jumping out of her chair a little bit. So, Graciela, I believe you said that indirect detection, or maybe it was Tim, that indirect detection would be a confirmation of dark matter and not a discovery. Did you say that?
Yes, I did. Because I think the astrophysical, but it's not a given. For example, if for the 3.5 kV line, if it happens to be there, if you can really map the line, the profile of the line, maybe that is enough to convince you that it is due to dark matter instead of because of the type of dispersion of temperature that this thing should. So it's not entirely a given. There are exceptions. But I think that the astrophysical uncertainties are so large that it would be difficult to claim a discovery by itself.
Maybe it's worth repeating something we said when we were talking by ourselves, which was that if you did see more than one signal from indirect detection and you could show that it was strongly correlated with our understanding of the J factor, that might be suggestive enough depending on how, what the signal was.
And let's see, I think it's fair to say that everyone's background to one degree or another is in particle physics. So I didn't hear any enthusiasm about modified gravity or anything. It was really, the title of the session didn't involve particle dark matter, but I didn't hear any enthusiasm at all for either strongly interacting dark matter or modified gravity or superfluid dark matter, solitons, nuggets.
Hey, I give you my 8-point definition of what is dark matter, right? It could be solitons, could be many other things. So I think but it would have to behave like dark matter in the early universe. There is no escape right now. After 2013, with the precision data that we have, the discussion has changed. And actually, there is nothing else that would, I think, mimic. Would mimic. Actually, you talk about this. It will have to be that behaves like dark matter. It's a weird, maybe some field that behaves like dark matter and so on.
So I do think that this is the opportunity for astrophysical probes of dark matter, because it's really remarkable how little we know about dark matter substructure at mass scales below dwarf galaxy scales, really. And even dwarf galaxy scales are not that well understood. And in many cases, if the dark matter subhalo is even somewhat less dense than a primordial black hole, all the constraints, you showed this plot of constraint on the fraction f as a function of the halo mass with these lensing constraints. Those can pretty rapidly go away, even if you get something moderately less dense than a primordial black hole. And so just the fact that the power spectrum of the dark matter is relatively little constrained on even big scales. And one of the questions that I have for the astrophysics community is how can we prioritize that? Just making measurements of the halo mass function to smaller scales for objects that are less dense than.
Well, I think one possible path to help address some of that issue is with JWST, we're going to look back to very early structure formation.
Yeah, that's right.
Look back to Z of 10, 11, 12, maybe even larger, and try to understand that.
Yeah, so I think there are
and also
possibilities.
in the era of 30-meter telescopes.
Yeah, there are.
Really going to be new instruments.
Yeah, pulsar timing is another possibility. Looking for redshift effects from transiting objects is another example. So there are possibilities. I guess one question is how do we prioritize that as a community for this very broad class of dark matter candidates that may not give rise to, may not have a large coupling directly to the standard model.
Okay, so in the 10 minutes remaining, we're going to open up to the audience, and we have the 3 world experts here on particle dark matter, and we can play Stump the Chumps. So let's see, Elena had her hands up first, and then we'll go to Risa. Elena. Stand up and use your outside voice, please.
So, of course, we all agree here we have to diversify vocabulary, but I want to remind you all the speculative theories that we are here.
Is there a microphone that?
I just wanted to say that we are here because of our own success, right? If the direct detection experiment wouldn't have excluded all this stuff, you probably would still be thinking of something else, right?
It's not only that, yeah.
Okay, so the WIMP has done something, which in my opinion has been to really push ourselves to build better experiment, and so to give you a lot of opportunity to think left and right. But to you, Catherine, specifically, I wanted to say all these new technologies that we know about, and they're wonderful, but one thing that I don't see, and we have to remember, is the demonstration of being able to see this extremely weak signature, namely the background. Because to me, the background that we have mastered in this big experiment is the main accomplishment. So these years have brought us not to find any particle, but to understand better and better how to fight the other ones that we surely know exist.
Yeah, and I think that's the reason why we're gonna, so I absolutely agree. Everything that we're talking about and looking beyond the WIMP in terms of detection is building on the enormous successes of constraining WIMPs. I mean, these technologies have been developed to such an amazing degree that now it's possible to talk about other detection channels. And it's also absolutely true that the devil is going to be controlling your dark count rates. I mean, this is something that Ruben and Sensei and Dominic, that's the thing that they're going to have to demonstrate. And at each step that we take down this road, the question is going to be, how well can you control your dark count rates? I completely agree with everything you just said.
Risa.
So I just want to agree with what Catherine said.
Thanks for using the microphone. If you turn it on, it's more effective.
But luckily, I have the loudest voice in the room. So I agree completely with what you said, that we should prioritize looking for substructure below 10 to the 8 or so. And I think there is a lot of effort there, but I think one of the biggest things that could help us prioritize that is for more particle physicists to say that they value it. And for us to talk together as a community between the astrophysics and particle physics communities to figure out, just all of the windows, regardless of,
Yeah, I completely agree with that. And it's something that I think now, so I think you should look for a change in the next few years.
Yeah, so I agree completely, and let's try to work on that change together and get it approved.
So
in the next
Risa, you're saying there should be an institute for particle astrophysics and cosmology somewhere that's effective?
That's effective, yes.
We had another question. Joe.
So I just wanted to make the case for a multi-messenger approach to the searches, multi-messenger approach for the searches of dark matter. For example, if we go to the heavy end, above TV, we're building CTA. We're also contemplating much more powerful accelerators, and they would mesh beautifully with multi-messenger approach to direct searches. I think the same can probably be said for the QCD axion range, where we're now exploring all these radio signatures. So I think we should be, do you think we should be using issues like this as we prioritize, because we obviously can't do everything. For the ultralight particles, directionality would be an amazing thing that also would help you. But with any experiment, you need confirmation basically from something.
Yes.
Yeah, I'd just like to know what's still left for QCD axion as
Wide open.
Wide open.
So that's actually one thing I had not fully appreciated is if you just look at the scan rates of the cavity experiments for axions, it's going to take many decades. I mean, we're going to need a lot of advances in technology to really be able to cover the entire QCD axion parameter space. And I went through these estimates recently myself, and if you just take like the scan rates that we have now, we're talking like tens of thousands of years.
But there is a plan to increase the scan rates by orders of magnitude.
Yeah,
That's
but
part of the plan.
it's still a lot of
They need to do
R&D. Yeah, it's still a lot of R&D. We still have a long ways to go on the QCD axion.
Okay, so we're out of time, and luckily I believe we have solved the question of the nature of particle dark matter. So let's thank the panel, and